Right, ladies and gentlemen, welcome. This is our discussion of our second secondary topic, in equilibrium, buffers. It falls right in the middle between common ions and weak acid or weak base titrations. And it's probably our most important secondary topic. It's the one that tends to come up the most. It's the one that requires probably the most conceptual understanding. And for that reason, this video is going to be not as many example problems, a lot more of quote-unquote Mrs. Julian talking, traditional notes, because before we get into calculations with buffers, you really have to understand what a buffer is and how it works. And then you can do the math with it, but the math really is secondary to understanding what is it that a buffer is and why does it do that, what's happening with buffers, etc., etc. Now, the nice thing about the math about buffers, and we're going to get there, is it really follows right on the heels of common ions. The math isn't necessarily the quote-unquote hard part about buffers. Where students typically need to work a little bit more is in their understanding of buffers, and that's why we're actually going to spend 3 days in class talking about buffers, doing things with buffers. So first up, what is a buffer? What is the definition of a buffer? A buffer is a solution that can resist change in pH when you add an external acid or an external base to it. The word to buffer means to prevent or to absorb or to kind of keep something from happening, like a buffer between two people might be an intermediary to prevent them from killing one another. Your bumper on your car acts kind of as a buffer sometimes. If you hit a tree, the bumper crumples so that you yourself do not crumple. So this word to buffer, we sort of see that in the definition of a chemical buffer in that it's resisting change in pH, that you're adding an acid to it, but the pH of the solution isn't really changing all that much. That's a buffer. Many solutions in life as we know it are buffers. Our blood is a buffer, and it's actually very important that our blood is a buffer solution because we need to maintain a certain pH level in our body in order to ensure that all our proteins are working correctly. A lot of our proteins are designed, and that includes enzymes. Enzymes are proteins. Are designed to work between a pH of around 7.2 to 7.6. So we need a buffered system so that if we as a person get exposed to, either through inhalation or ingestion or simply like external exposure, if we get exposed to an acid or a base, which happens a lot because acids and bases are pretty prevalent, that won't change the pH levels in our blood all that much, meaning we can be exposed to a small amount of acid and base, but it's not going to affect the way our body runs, which if it did, would basically totally screw up all our enzymes and cause us, to start to shut down. How do you make this buffer, this solution that can resist change in pH? The key to making a buffer is really this. You absolutely have to have a weak acid and its conjugate base. That is what a buffer is consisting of. That's how we get this solution that can resist changes in pH. You need to have both of them together. So this is really sort of a critical part of our buffer. But that second part, it's not just having the weak acid and its conjugate base pair there. We have to have a lot of it. We have to have a lot of it. Our buffers, you've got to have both there, the weak acid and the conjugate base together. You have to remember, and this is crucial, that a weak acid will not react with its own conjugate base. HA does not react with A minus. They're essentially ambivalent to one another. They're like, hey, what's going on? They don't react with one another because they're flip sides of the same coin. So you've got these two things together that do not react, but one's an acid, one's a base, and together they can prevent the whole solution from changing in pH too much. You need a lot of them because you need a lot there to anticipate possible external acids or bases being added to it and to kind of deal with that. How are you going to recognize a buffer if you have a buffer solution in front of you? Well, ideally, and this is ideal, you want to pick the solution that's got, via this definition, a weak acid and its conjugate base together, because if you've got that together, then you know you can resist changes in pH. In order to do that, remember, you have to stop seeing ionic compounds as one thing. So you want to look for an ionic compound that contains a common ion. And here's where, this is why we're talking about buffers after we talked about common ion problems, right? You're looking for the thing that it has in common, the weak acid and its conjugate base. It's unlikely that the conjugate base will be a compound on its own. It's much more likely that it will be part of a salt, like HA and A minus. Well, you can't go out and just buy A minus. It's got to be attached to something that's positive, like sodium. The sodium ion, that's positive. So you can go out, you can buy NaA. You can't buy A minus, because it's why it's going to attract anything that's positive around it. So you want to look for that common ion. See, ionic compounds is the two ions that go into them, and look for the thing that they have in common. Now that's absolutely ideal, however, but what if, you know, you're looking at your possibilities for buffers and you don't see any pair that's got a weak acid and its conjugate base together? Well, then there are some other ways that you can actually generate a buffer if you don't start with the weak acid and its conjugate base at the same time. If you do start, and those are if you have a weak acid and a strong base, or a weak base and a strong acid. If you have a weak acid and a strong base, for example, you can actually get a buffer from that combination. And the way that you do that is you take some of the weak acid and you react it with the strong base, because when that happens, you're going to create the conjugate. And once you create the conjugate, then you can pair it up with the original weak acid. As an example, when I say weak acid and strong base, let's say you have HA and NaOH. And you want to make a buffer from this. You can. You absolutely can. You already have half of what you need, which is the HA. So maybe you save some of that. And then you take some of your HA and you react it with your sodium hydroxide. When that happens, well, HA is an acid, sodium hydroxide is a base. They're going to neutralize one another. Neutralization does not mean pH of 7. I know we call that neutral, but a neutralization reaction is simply an acid and a base reacting until one of them is done. One of them's gone, kind of like our BCA chart. You know, you make the smaller one go to 0. So this will create, when these things react, it'll create water, which is fine, but then it would also create that NaA, right, from the HA and then the sodium hydroxide. And notice I did draw this as, one way, not equilibrium. That's going to be important later. Here, right there, you've created A minus, which is the conjugate of HA. So if you still have some HA left over because you reserved it, and you combine it with your HA, there you go, that's your buffer. So you just basically, in order to create a buffer, it's okay if you're not starting with both the weak acid and its conjugate base right at the beginning. You can get basically the weak acid to generate its conjugate base, and then combine it with some additional weak acid, and then there you go, there's your buffer. There's the combination of the two. Now, the addition of an acid or a base to a buffer. So now we're moving from making the buffer to, okay, we've made this buffer. What happens when you add stuff to the buffer? When a small amount of base is added, and when I say base being added, I mean an external base. For example, sodium hydroxide. So you have your weak acid and its conjugate together, and then you're adding some additional sodium hydroxide. The sodium hydroxide basically has two options in your buffer, because you've got two things. You've got the weak acid and you've got its conjugate base. You've got two components to your buffer. Your sodium hydroxide is going to choose which one it's going to react with. Well, NaOH is a base, so obviously it's going to react with acids, because that's what bases do. They're really good at that. So the sodium hydroxide reacts with the weak acid in the buffer. And we're going to look at that reaction on the next slide, specifically on what's happening there. But when the sodium hydroxide does that, it's going to wind up making your buffer slightly more basic. So it will raise that pH. But it won't raise the pH all that much. It won't raise it as much as if you added sodium hydroxide to a non-buffered solution. It will raise it. It's just going to raise it a very small amount. And then we have the flip side. If you take a buffer, your weak acid and conjugate base together, and you add a small amount of external acid, like hydrochloric acid, So this isn't the acid that's in the buffer, this is acid coming from the outside. Again, that acid has two choices. There are two things in the buffer, weak acid and a conjugate base. What is it going to react with? It's going to react with the base. Of course it is. That's what acids do. Acids are proton donors, bases are proton acceptors. They love to react with one another. So the acid that you add from the outside reacts with the base component of the buffer, and it will make your buffer slightly more acidic. But it won't make your buffer nearly as acidic as if you had added that external acid to a non-buffered solution. So it does change the pH. It doesn't totally resist changes in pH, but it makes the change in pH a lot smaller than it would have been otherwise. Now let's really look in detail at what happens when you add that external acid or base to your buffer. So in looking at this diagram, there's kind of a lot to unpack. I want you to start sort of focusing here at the center of the diagram, because that's where we're starting. We're starting off with our buffer. And notice we do have a buffer because we have HF and we have F minus together. These two things do not react with one another. They're conjugate pairs. They're ambivalent towards one another. They're flip sides of the same coin. They don't react with one another. So we have a buffer. We have a weak acid and its conjugate base, and we're starting out with equal concentrations of those two things. We know that if you kind of look where this little dashed line is, it's showing that we've got the same amount of HF and F minus. If you look down here, and we look at this particle diagram, we've got 5 HFs. That's this thing, right? HF, and then we have 5 F minus. That's this thing. Now, to that buffer, we're going to add hydroxide. So this is external base that we're adding in. And let's say that this is coming from sodium hydroxide. Well, what will happen? You're adding NaOH, sort of it can react with either of these two things. It is obviously going to react with the HF, and it's not going to react with the F minus. Bases don't really react with bases. They react with acids. So what does that reaction look like? It's shown right here in this little arrow. Several things that I want you to look at in this reaction. Number one, this is your sodium hydroxide. That's the OH minus. So that's the NaOH. It's just shown in ionic form. Now it's reacting with the HF. Huge point. This is a one-way arrow. Your HF is going to react with the sodium hydroxide until it's gone. Neutralization reactions are one-way reactions. This is not an equilibrium reaction. Neutralization reactions go until something is totally used up. But we have to sort of pay attention to what it is that we're creating. Let's look at the products. Well, this is neutralization. So your HF donates a proton to the OH minus. What do we generate from that? We generate water. Okay, that's water. We know that water is safe. What else do we generate? We generate some F minus. So looking back up at the bar chart, essentially, you see that we had to use up some of our hydrofluoric acid in order to get this to happen, right? So some of our HF is gone, but only a little bit, right? We didn't use up a lot of HF. And then notice right here, we created some more F minus, right? So the amount of F minus that's in our buffer has gone up, but not substantially, just a little bit. But think about what we did basically by doing that. You took some added sodium hydroxide. Oops, sorry, going back here. You took some external sodium hydroxide, which is kind of a scary base, and then you neutralized it. You neutralized it by turning it into, instead of a scary base, a weak base. You took that NaOH into that buffer. The buffer reacted its own acid with that base and turned it into its own base and turned it into a weak base. So basically you turned your strong base, right here, your OH minus, into a weak base. thereby causing a much smaller change in pH than you would have if that hadn't have happened. Weak bases have much less impact on pH than strong bases do. Strong bases will dominate, but your buffer sort of took that strong base and covertly turned it into something that's a lot wimpier. Thereby, it has a lot less effect on pH. If you look at the particle diagram, so I'm going to erase a little bit of this right here. If you look at the particle diagram right here, and you see what it is that we ended with, we started with 5 HFs and 5 F minuses. Well, we created one additional F minus, so you see we've got 6 F minuses over here, and we had to use up some of our HF, so we only have 4 HF. But we still have some HF that's there in solution that's sort of ready to go and continue working as a buffer. Looking at the other side, so again, we're starting in the middle with a buffer, equal concentrations of acid and its conjugate base, HF and F minus, and to that, now, instead of adding sodium hydroxide, we're going to add an external acid like HCl. So this H plus that's right here, this is not the H plus that we're getting from the HF. This is H plus that's being added from some external acid source. Again, if we look at the particle diagram, we start with 5 HF and 5 F minus, but what happens now when we add the acid? Well, here we're looking at the reaction that's written in the arrow. We're adding HCl. What is the HCl going to react with? It's going to react with the base. So it's going to react with that F minus. So that's what we're seeing in this arrow. Now this HF right here, remember that's HCl. That's a strong acid. And what's written in that arrow is a neutralization reaction. It might not look like one to you, but it sure as heck looks like one to me, because I see a strong acid combining with a weak base, and I see them doing what acids and bases do. The acid is donating its proton, its H+, and the base is accepting the proton. That's what bases do. But we're generating HF, and HF is a weak acid. So we've taken that strong acid that was added, that hydrochloric acid, that 100% dissociation that, you know, I don't really want to encounter in my daily life at home. You know, there's a reason you don't have hydrochloric acid all that often in your home. And the buffer, through this one-way reaction, right? This doesn't go backwards. This just goes forwards until one of your reactants is gone, takes that strong acid, turns it into a weak acid, which has a much smaller impact on the overall pH of the solution, thereby resisting change in pH. You have generated some more of your HF. Yeah, you've made a little bit more, and yeah, you lost a little bit of your F minus, but overall, you still have about the same approximate ratio of HF to F minus, but you no longer have that scary hydrochloric acid there. You've turned it essentially into a component of the buffer. That's what buffers do. And then looking at the particle diagram here, that's showing us using up some of our F minus. So now we only have 4 F minuses, but we made an extra HF in this process. Why do buffers work? How can buffers resist the change in pH? Just sort of saying in words what I said on the previous page. Buffers, by definition, resisting change in pH, they do that via what I call mopping up the strong acid and the strong base. They kind of ingest it and spit it out, and when it comes out, it's no longer a strong acid or a strong base, it's a weak acid or a weak base. Because, and the reason they do that, is that neutralization reactions are one-way reactions. You need to get it out of your head that neutralization means having a pH of 7. That's not what it means. A neutralization reaction is simply where an acid does what an acid does, meaning an acid donates a proton. Who does it donate it to? It donates it to a base. We're going to see that we have neutralization reactions that do not have a pH of 7. They're still considered neutralization because we have an acid that donates a proton to a base. That's neutralization. That's Bronsted-Lowry acid-base chemistry. Once that strong acid and strong base is neutralized, it doesn't reform. That's that whole thing where it completely dissociates. If you take HCl, you turn it into H plus and Cl minus, it doesn't go backwards. That's because HCl is a strong acid. Complete dissociation prevents reassociation. So as long as you can get that H plus kind of out of there by turning it into that weak acid, you have neutralized your strong acid. But the thing is, your buffer can't keep doing this indefinitely. You have to have a large amount of your weak acid and your conjugate base pair. So you need, in that prior slide, a large amount of HF and a large amount of F minus. You need a big amount of that in order to make a buffer. You can't it won't work if you take, for example, 10 milliliters of HF and 10 milliliters of F minus, combine them in your tiny little beaker with your 20 milliliter solution, take an enormous 3-liter jug of 6 molar hydrochloric acid, pour it into your tiny little 20 milliliters and say, ha-ha, resist this change of pH, mofos. Yeah, it's not going to work. It won't work. You need a large amount of weak acid and conjugate base in comparison with the amount of acid and base that you're adding from the outside. Buffers are good in resisting changes in pH for small amounts of acid and base addition. You try to overpower your buffer with an enormously large amount of a concentrated strong acid, strong base. Yeah, your buffer's not going to work. It's not going to work, but it will work for sort of small amounts. Now, buffer capacity is essentially saying just that. How much acid or base can your buffer absorb before its pH starts to change dramatically? And typically speaking, scientists agree that a pH change of 1 unit is considered a significant change. So how much acid or base can your buffer handle before the pH changes by that 1 unit? And this is dependent on basically how much weak acid and how much of its conjugate base you have in solution. This should hopefully make some inherent sense to you that the more of the stuff that goes into your buffer that you start with, the more weak acid, the more conjugate base, the better your buffer will be at resisting change in pH, and that's absolutely true. The more HF, the more F minus, in that example that we saw in the diagram that you have, the better it is at resisting change in pH from an external acid or base addition. pH range. All buffers are not effective at buffering over any pH range. It's specific very much to the acid that is the main component, basically half of your buffer. It's dependent on the Ka value for the acid. Buffers work best when you've got the pH range that you want to maintain it around. So like for blood, for example, blood wants to maintain pH between about 7.2 and 7.6. Our body isn't really interested in maintaining its blood between a pH of 4 and 5, so we're looking at a different pH range. So the acids that our body has sort of chosen to use through evolution have been those with Ka values that will give pKa's that are slightly above 7. Remember, pKa simply means the negative log of the Ka value. A lowercase p in front of anything is actually a mathematical function. It's telling you to take the negative log of that thing. That's why pH is the negative log of the H plus concentration. You're taking the negative log of H. POH is let's take the negative log of OH. PKW, take the negative log of KW. PKA, take the negative log of KA. So you want to pick a buffer, if you're making a buffer, that has an acid in it whose pKa value is fairly close to the range at which you want this thing to resist changes in pH. Now, for buffer calculations, the nice thing is that they're kind of the easy part of buffers. They're a little bit less involved, well, I shouldn't say less involved, but they're based on things that you can already do. They truly are simply common ion problems. If you go back to my common ions video and you'll have a look at those example problems with acids and bases, you'll look at what's there. You have a weak acid and a conjugate base together at the beginning of the problem. Initial concentrations of weak acid, initial concentrations of conjugate base. You know how to solve that problem. It's exactly the same. So it's, you know, the equilibrium method. You write a reaction. HA goes to H plus A minus. You fill in an ice chart. You know an initial concentration of HA. You know an initial concentration of A minus. Fill in that ice chart, minus X plus X plus X. Make your assumptions. Go to your equilibrium expression, plug in, write a buffer. As long as you've got that HA and that H minus together, you know you have a buffer. That's how you make a buffer, how you make a solution that can resist changes in pH. So you already know how to do this. It's absolutely no different. The only thing that would be different is it might say the word buffer in the question, but that's it. I mean, I could absolutely take those questions from the Common Ions video and turn them into buffer questions basically by adding the word buffer in the problem, and you would know how to solve them. It is no different. So I'm not going to go through that. Instead, I'm going to show you the Henderson-Hasselbalch formula, because this is an alternate method for solving buffer problems and looking at pH. No, it's not Henderson-Hasselbalch. No, this is not a Baywatch formula. It's the Henderson-Hasselbalch equation, which I will abbreviate as HH, because it's kind of a mouthful. And it is it's derived from equilibrium. It's derived from the equilibrium expression and the relationship how Ka equals H plus times A minus over H. Ka equals H plus times A minus over HA. That's where it comes from. And it's basically just a slightly fancy rearrangement of that. This right here is the Henderson-Hasselbalch equation. pH equals pKa plus the log of A minus over concentration of A minus over the concentration of HA. This is on your reference table. Yay! You don't have to memorize it, and I will, encourage you to use it. However, you need to know when you're allowed to use this. I am now granting you permission to use the Henderson-Hasselbalch equation whenever you think you can in an equilibrium problem. But you have to understand that you cannot use this for any equilibrium problem you want. You can use this when you have a buffer. How do you recognize a buffer? If you have A minus and HA. They both have to be there. A weak acid and its conjugate base. If you are going through a problem and you realize that that is indeed what you have, that you have HA and A minus, and they're both there at the beginning of the problem, right? You have initial concentrations for both of those things, then by all means, use the Henderson-Hasselbalch equation to get your pH. But you cannot use the Henderson-Hasselbalch equation if you only have one of them. If you only have HA, yeah, you got to go through the equilibrium problem, ice chart expression, solve for H+. If you only have A minus, same thing. Ice chart expression, solve for OH minus. This does not work on KSP. No, you can't do it. And we're not going to use this for Kc. This is for buffers. So you've got a weak acid and its conjugate base. You must have them both together, and then you can use the Henderson-Hasselbalch equation. Now, a couple questions about this before we do an example problem. What would be the pH of a buffer where the concentration of the weak acid is equal to the concentration of its conjugate base? Well, let's think about this. I'm basically focusing on this final component of the Henderson-Hasselbalch equation, right? If A minus equals HA, then we're talking about a fraction that, I don't know, looks like this, right? X over X. Well, X is the same as one another, so that's 1. So we're talking about taking the log of 1, right? What's the log of 1? If you do not know automatically off the top of your head, and you can't do this and you're going to your calculator right now, if you cannot tell me what the log of 1 is, you have to go and read the section at the back of the textbook in the appendix that explains log rules. Because if you do not know that the log of 1 is 0, you got to play some serious catch up in terms of feeling comfortable with doing this type of math. This is math you are expected to be able to do without a calculator on the multiple choice. Feel comfortable working with logs. There's a section in the back of our book that walks you through how logs work. Look at it. Read it. This is math I am anticipating you already know. Log of 1 is 0. HA equals A minus. So what's the pH of a buffer where HA is equal to A minus? Well, it's going to be equal to whatever pKa is. And that's actually a very special point. It's called the half equivalence point when HA is equal to A minus. And yeah, that's a titration term, right? Equivalence point, half equivalence point. That's going to come back when we're talking about weak acid or weak base titrations. So that's of significance, and I'm kind of alluding to it now, and we'll look a little more in depth at it in the third of our secondary topics. All right, 2 practice problems with buffers. First up, calculate the pH of a buffer composed of 0.12 molar benzoic acid and 0.20 molar sodium benzoate. The Ka for benzoic acid is 6.3 times 10 to the minus fifth. Now, you can absolutely solve this problem by writing a reaction. You're going to write a Ka reaction. You've got your benzoic acid goes to H plus the benzoate. You're going to fill it. You can fill in an ice chart. We have the initial concentration of the benzoic acid, that's 0.12 molar, and we have the initial concentration of the benzoate. Right here's where you see sodium benzoate, and I don't really want you to see the sodium bit. I want you to focus on the benzoate bit and recognize that that's the conjugate of benzoic acid. It's a common ion. You're not starting with 0 for that. You're starting with 0.2 molar for that. You can fill in an ice chart. You can go to a K expression. You can plug into your K expression and you can solve for H plus, get pH that way. You already know how to do that. If that's the method you want to use for this problem, it's not wrong. Go ahead and use it. But I'm going to demonstrate the Henderson-Hasselbalch equation instead and see how we can use this to get the answer as well. Now, Henderson-Hasselbalch, again, it's pH equals pKa plus the log of A minus over HA. Now, we are allowed to use that here because we have both of these things. We have the weak acid, that's the benzoic acid, and we have its conjugate base, that's the sodium benzoate. So because we have both of them, a weak acid and its conjugate base together, great! We can use the Henderson-Hasselbalch equation to get our answer. So then it's just plugging in. So pH is equal to pKa. That's the negative log of the Ka value. So the negative log of 6.3 times 10 to the minus fifth. Plus the log of A minus, that's your weak base. Okay, weak base, that's the benzoate. So we're going to do 0.2 molar on top, divided by the concentration of the weak acid, that's the benzoic acid, so that's 0.12 molar. Make sure you know which is which. The formula is on your reference table, A minus over HA. There's no excuse for getting it wrong. Make sure you know which is the weak acid and which is the conjugate base. And then it's just solving. I do recommend students, I'm sort of encouraging you to do some intermediate steps and to not try to skip right to the answer. So like I like to write down what the pKa value is. So when I take the negative log of the Ka, I get 4.200, and then the log of 0.2 over 0.12, I get 0.222. So adding them together to get the pH of this buffer, I get 4.422. And what I want to point out about this, I mean, first of all, it's your answer and you're done with the problem, so that's kind of nice, is that we do not have our pH equaling pKa. It does not here, and the reason it doesn't is that we do not have the same concentration of A minus and HA. We actually have a little bit more, looking at our concentrations, a little bit more of the weak base. We've got just under double the weak base than we do conjugate acid, 0.2 molar versus 0.12. So we see in this final pH right here that, you know, the final pH is a little bit higher than the pKa value, right? pKa is 4.20 and we've got a pH of 4.42. That makes sense because we have slightly more base than we do acid, so we expect a slightly more elevated, a higher pH, indicating it's slightly more basic. All right, and then one more problem. This is on preparation of a buffer rather than what is the pH of the buffer, but we can still use Henderson-Hasselbalch to get it. Calculate the mass of sodium acetate required to prepare a buffer of pH 4.55 when added to 0.5 liters of 0.67 molar acetic acid. Ka value for acetic acid is 1.8 times 10 to the minus fifth. Wow, that's a lot of numbers. I'm going to start off with the Henderson-Hasselbalch equation. And the reason that I'm doing that is because they said the magic word in the problem, buffer, which basically as soon as anything mentions buffer, then it should be kind of automatic. Hey, let's see if we can use Henderson-Hasselbalch. And let's start thinking about these numbers that we've been given. They're asking us for the mass of sodium acetate. Is sodium acetate an acid or a base? Well, hi, it doesn't start with an H, so guess what? It's a base. So we're looking for basically the mass of the weak base. That's what this question is asking. How much weak conjugate base do we have to add into all this stuff so that we can make this buffer under these specifications? What other numbers do we have? Let's see. They give us pH. Oh, look. pH. That's in our Henderson-Hasselbalch equation. When added to 0.5 liters, oh, that's volume. Oh, that's interesting. We've got molarities, so I bet we're going to be using that somewhere with molarities, of a 0.67 molar acetic acid solution. Acetic acid, that's a weak acid. Okay. It's right there. We've got that. Check. We have the concentration of HA. And then it says Ka value for acetic acid, 1.8 times 10 to the minus 5th. Oh, Ka right there. So kind of looking at the information that's been given, that they're asking for the mass of the sodium acetate, it should be getting obvious to you that we want to solve for this A minus. We have pH, we can easily get pKa, and we have HA. We need to be solving for A minus, and that's exactly what we're going to do. So then it's just plugging in, and the rest of this problem, honestly, is math. Not so much chemistry, much more math. So 4.55, that's the pH that we want, is equal to the negative log of 1.8 times 10 to the minus 5th plus the log of A minus, that's what we're looking for, over 0.67 molar. If we take the negative log of 1.8 times 10 to the minus 5th, you should get 4.74 when you do that. So I'm going to kind of go to that next bit where I have subtracted that from both sides, and we get negative 0.19. Be very careful of your signs here because negatives change things. Negatives are important. You know, we've got to keep those signs there. It'll mess things up if we don't. Is equal to the log of A minus over 0.67. Solving at this point, here's where you have to know your log rules. You just have to. There's no such thing as dividing both sides by a log in order to get rid of the log. You have to do an anti-log. If you're looking at this and you're like, I have no idea what to do from here, read the section in the textbook, back of the textbook. There's a whole appendix where it talks about log rules. Read it, know it, love it. It's your new best friend. This is math that I expect you to know how to do. So we're going to raise both sides. We're going to make them the exponent for 10. We're doing the anti-log, this whole base number power thing. And so if we raise both sides, make them the exponent of the power for 10, then we are going to eliminate the log and simply be left with the stuff that's in parentheses. So I'm going to erase what we have thus far, basically because we just need the work. It's kind of a long problem. It's not really a hard problem, it's just long. So when you do 10 to the negative 0.19, you get 0.646, and that's equal to our A minus concentration over 0.67 molar. Solving for the A minus concentration, we get 0.433. Now, that's nice, that's not our answer. A minus, what does A minus mean in this problem? Well, A minus is the conjugate base. The conjugate base is the acetate ion, right? The weak acid is acetic acid, HC2H3O2, so the conjugate base is the acetate ion, C2H3O2 minus. We're looking for, however, sodium acetate. So then you have to consider what the relationship is between sodium acetate and the acetate ion. They're in a 1-to-1, right? Sodium acetate, you put it in water, it completely dissociates into Na plus C2H3O2 minus. So this thing is in a 1-to-1 with our sodium acetate concentration. So therefore, I know that 0.433 molar is the concentration of sodium acetate that I'm looking for, right? I know this is similar to the KSP problems in that regard. So I've identified that that's the concentration I want of the sodium acetate, but we're looking for the mass. Well, how are we going to do that? That's where our volume is going to come in. I'm going to use the molarity, 0.433 molar. Is equal to X moles of sodium acetate divided by the volume of the solution, which is 0.5, so that I know that I want 0.216 moles of sodium acetate. Yay! Not done though. One final last step. Turn the moles of sodium acetate into grams of sodium acetate via gram formula mass, which at this point should be easy as pie for us. And we get that we need 17.7 grams of that sodium acetate in order to create this buffer to these specifications. So that's just using the Henderson-Hasselbalch formula to make a buffer rather than determine the pH of one.